Welcome back to the physics class, my dear students. So that as you were studying in the previous class, that is what the linear magnification derivation of the compound microscope. So that I said just give the working principle and the linear magnification formula for a compound microscope when the final image is formed at the least distance of distinct vision. So my dear students, I already explained you the construction as well as I even explained you the working principle of the compound microscope when the final image is formed at least distance of distinct vision. With that, dear students, today we are just moving towards the derivation of the linear magnification of that case. So in the previous class, we just derived the linear magnification formula for the eyepiece. But still it's left over that we should derive the expression for the linear magnification of objective lens. So then we can come towards the finally the total magnification of the compound microscope. Now my dear students, just as you know that the lens, that is what the compound microscope is made up of two lenses. Two lenses are said to be the convex lens, whereas those two lenses are exactly placed coaxially to each other, whereas these two lenses are mounted on the two ends of a sliding tube. Whereas now, the lens which is having a less focal length and the lens which is placed towards the object is called as objective lens, and the lens which is placed towards the observer is called as eyepiece. Eyepiece is the one which is having greater focal length. Now my dear students, according to the working principle, we are just going to place an object just beyond the principal focus. It means just beyond, it indicates that it is very near to the principal focus. Now my dear students, the distance between the optic center and the object A, B is considered as the object distance written as U. U naught represents that the object distance of objective lens. Now according to the rules of formation of image, so that when a parallel beam of light incident, it passes through the principal focus. Similarly, that is said to be the principal focus is here, so that this is the principal focus of objective lens. And I am considering another one ray which is passing through the optic center. After refraction, it passes without bending. So that we are going to meet at this point, so that when the object is placed beyond, just beyond, so it is very near to that point. So just beyond this focus, principal focus of objective lens, then the real inverted image is formed beyond 2f naught on other side of the lens. So that here it is said to be A dash and B dash. Right. Now here one, see this is an image for the objective lens, so that the distance between this image formed by the objective lens and the optic center is called as the image distance, represented by B naught. Now my dear students, now see you can observe, whereas this is even called as the length of the microscope, whereas this exactly comprises the distance between the two ends of the microscope, that is what the first convex lens and the second convex lens, that is what the objective lens and the eyepiece. So that we can say this B naught is also called as the length of the microscope. Now my dear students, this image which is formed by the objective lens acts as an object for second lens, that is eyepiece. Now the distance between the eyepiece and this object A dash B dash is adjusted such that the image, the final image is formed at is formed at least distance of distinction, whereas the final image is represented by A double dash, B double dash. Therefore, already we said that the final image is formed at the least distance of distinct division, whereas the least distance of distinct division is represented by capital D. And you know that the least distance of distinct division is always equal to 25 centimeter. So here the observer is present. So that, my dear students, this is about the diagram that we discussed, and you can observe that here at the principal focus the object is present, whereas you got an image at least distance of distinct division. See, my dear students, in the previous class we even discussed the simple microscope. There we discussed the linear magnification case of the simple microscope. So in that derivation of the linear magnification, again we consider the two different cases. That is what? The image is formed at the least distance of distinct division when the object is placed at the principal focus. And the another case is that the object, when it is placed exactly at that principal focus, the image is formed at the, what we can say, that it is formed at infinity. So we have the two different cases. So but for the case when the image is formed at the least distance of distinct vision, then this eyepiece is going to act as a lens. The eyepiece is going to act as a simple microscope. It is acting as a simple microscope. Now magnification of a compound microscope. See that the magnification of the compound microscope, right? Completely I am just writing here it as CM, so that can be written as M is equal to product of the magnification of the objective lens and the magnification of eyepiece. Now let us calculate the magnification of eyepiece first, so that the magnification of eyepiece ME is equal to 1 plus D by FE, where D is the least distance of distinct division, FE is the focal length of eyepiece. Yes, students, keep in your mind that this we got from the simple microscope derivation. Similarly, now let us see the magnification of objective lens. Yes, see here, before writing this formula, we should write here in the bracket, so that eyepiece acts as a simple microscope. Eyepiece acts as simple microscope, so that from the previous derivations we know that when the image is formed at least distance of distinct vision in case of a simple microscope, so that the magnification can be written as 1 plus D by F. So just return the same thing here. Now let us move for the objective lens. Is what the magnification can be written as, you know that B by U. But here we are calculating the magnification for objective lens, so that I am just writing it as M naught. What is M naught? It indicates the magnification of objective lens. So V naught is the image distance for the objective lens, and U naught is the object distance for the objective lens. Let us see here, whereas V naught is an object distance for the objective lens, so image distance for the objective lens, but whereas V naught is equal to L, said to be the length of microscope. So my dear students, V naught is equal to L, called as the length of microscope. The length of microscope. So as I already said you that the distance between the two lenses comprises the length, so that V naught is equal to L. Then see carefully. So what is U naught here? So I just said you already. We placed an object AB just beyond the principal focus. Just beyond. It means this object is very near to F naught. So what I am just going to write here, this U naught becomes equal to that of the focal length. Why? Because the distance between the optic center and the principal focus is called as the focal length of the objective lens, represented as f naught. And here students, here u naught is the distance between the object and the optic center, but whereas in the working principle, we said that the object is placed just beyond the f naught. It means the object is very close to f naught. So I am just considering the distance as the focal length. So that u naught is equal to f naught. U naught is equal to f naught. Dear students, keep in your mind. So you can observe carefully that. Here, what is v naught? See, you know the real image and the real object distances are taken as positive, and the virtual image and the virtual object distances are taken as negative, and all the distances should be measured along the direction of incident ray. If the distances which are measured are opposite to the direction of incident ray, they should be considered as negative. So according to the sign convention, my dear students, here you can observe that V naught is measured along the direction of incident ray. So here the direction of incident ray is towards right side, whereas we are measuring a V naught towards the right side itself. So that, but here we are calculating U naught opposite to the direction of incident ray, whereas incident ray is towards right side, I am measuring it towards the left side. So I can say that U naught is negative sign. So U naught is equal to minus f naught. So I am substituting it here. So m naught becomes equal to minus L by f naught. Take it as equation number 3. Now let us put the equation 2 and equation 3 in equation 1. Yes. Now put equation 2 and equation 3 in equation 1. Let us see what will happen. So that m is equal to, what is m naught? It is minus L by f naught into what is me. So that 1 plus d by fe. So this is the final linear magnification formula for the compound microscope. My dear students, you can observe it carefully and you can explain the terms which is present in that. So that here L is said to be the length of microscope, f naught is said to be the focal length of an objective lens, d is the least distance of distinct vision, and f is the focal length of eyepiece. What is this negative sign indicates? Where negative sign indicates that the image is inverted. So my dear students, ಇಲ್ಲಿ final image ಬಂದಿತ್ತು invert ಆಗಿತ್ತು, right? So that the minus sign, the negative sign indicates that the final image is inverted with respect to the object. Here I have already shown you. So you have the diagram in your book, right? So observe the diagram. So here we have the object, whereas with respect to the object, the final image is inverted. That is what the negative sign indicates here. So this is about the compound microscope and also the linear magnification formula related to the compound microscope. As that we already discussed in case of a simple microscope, that there also we discussed the two different cases. That is what the final image is formed at the least distance of distinct vision, and the second case is that when the final image is formed at infinity. Now my dear students, similar to that of simple microscope, in case of compound microscope also, we are just moving towards the explanation of the formation of a final image at the infinity. Dear students, take down the next heading that give the working principle and the expression for the linear magnification of a compound microscope when the image is formed at infinity. Hope you return this. Just pause the video and write the heading that what I said. So now, first let us explain that. See, I am discussing the case in which the image is formed at infinity. The image is formed at infinity. Give the expression for linear magnification and the working principle of the image formed by the compound microscope at infinity. As well as we can explain it with the help of ray diagram also. First, let us move on for writing of the ray diagram. Dear students, as you know the construction, I am moving with the same construction that in case of a compound microscope, always we have two lenses. I am just placing the two lenses here. So the lens, yes, here I am placing the two lenses. Yes, these are the two lenses I am going to place, right? So how to construct these two lenses? These two lenses are placed coaxially. It means the axis of both the lenses should be parallel with each other, right? Now, whereas these two lenses are mounted on either side of an adjustable tube, metal tube, right? And you can observe it. The lens which is having lesser aperture, the lens which is having less focal length is considered as the objective lens, and this lens is placed towards the object. And you can observe that we have another one lens, so that lens is having a greater aperture, that lens is having a larger focal length. The lens with greater focal length and the greater aperture and which is placed towards an observer is called as eyepiece. Is called as eyepiece. Yes, it's clear now. But now let us move on for which one, as well as we can arrange the distance between, we can adjust the distance between this two lenses, these two lenses, just by using a rack and pinion arrangement. That is what we can just use a screw so that we can adjust the distance between this objective lens and eyepiece. Okay, then what is the working principle beyond this compound microscope at which the image is formed at infinity? Yes students, here also I am just going to place an object. First let us see the ray diagram. Afterwards I used to explain the working principle. See, I am going to place an object. Let us name the object as AB. AB is said to be the object. Then the distance between the optic center of the objective lens and the object is called as the object distance, represented as U0. Now the object is placed just beyond F0. Next, the distance between the optic center and the principal focus of the lens is called as the focal length of objective lens, written as small f0. I am using a parallel beam of light which is parallel to the principal axis. When it falls on the lens and it refracts and passes through the principal focus. It refracts and passes through the principal focus of the objective lens. See my dear students, whereas the distance between the optic center and the principal focus is called as the focal length f0. Now I am going to use another one ray which is passing through the optic center, so which passes out without refraction. I am just going to represent it clearly. Yes. Now you can observe that. So it passes without refraction. So where the image is formed, exactly if the object is just beyond, the principal focus, then the image is formed beyond the center of curvature, beyond 2f0 on other side of the convex lens. So here the image is formed, whereas the image formed is real because after refraction the rays of light are going to meet at a point. As well as if it is real, it's obviously we can say that it is inverted. Now let us name this object as A double dash and B double dash. Right. So A dash, B dash. Now my dear students, now you can observe that. See the distance between. See, it should be in that way. So So this position of the image which is formed. The position of the image which is formed is to be arranged is to be arranged in such a way that just by using a random linear arrangement, we should adjust the distance between A dash, B dash. That is what the image of the object lens and the object of eyepiece, so that the distance between these two things are arranged in such a way that the image should be formed at infinity. When we will get the image of infinity, when this object is said to be exactly at the principal focus. Now my dear students, see here I already represented f naught. I will just represent this image system. That is what the distance between the image formed by the objective lens and the optic center is called as the image distance, represented as v naught. Right. Now the distance between the object of the eyepiece, that is A dash, B dash, and this eyepiece is adjusted such that the object is said to be exactly placed at the principal focus of this eyepiece. Now, supposing the object is at eyepiece, you know that the images formed at infinity. So if the object is at principal focus, then the image is exactly formed at infinity. Yes. So with this arrangement, we are now moving towards the calculation of linear magnification. Right, my dear students, here we have V naught and also Fe. Whereas as you just discussed in the previous diagram, so that V naught is said to be the length of the microscope. Now this point is said to be the principal focus of the eyepiece Fe. Now let us see the working principle. I am just going to write the working principle now. So let us move towards the writing of working principle. Yes, what is the working principle? So my dear students, when the object is placed just beyond the f naught, the image is formed on other side of the lens beyond 2f naught, whereas the image formed is real and inverted. Now the image of objective lens acts as an object for eyepiece. The distance between the object A dash, B dash and the eyepiece is adjusted such that the image is formed at infinity. So take down the working principle. I am just going to write when the object is placed just beyond f naught, then on the other side of the lens, on other side of the objective lens, the real inverted right image is formed at beyond 2f. This is exactly the objective lens. It's to objective lens for that. Next, let us move on to eyepiece. So whereas the distance between A dash, B dash and the eyepiece is adjusted. So before that, the image of an objective lens acts as an object for eyepiece. So that's very good. So that the image A dash, B dash of objective lens acts as object for eyepiece. Now let us arrange the distance between these two things. Eyepiece. Then the distance between A dash, B dash and eyepiece is adjusted to get the final image. to get the final image at infinity, right? Yes, this is what the working principle of the compound microscope. So in this case, we are just going to observe the image formed at infinity. Now let us move for the derivation of formal expression for linear magnification case. My dear students, this is a very easy case to discuss. Why? Because we don't want to explain much, because we know that the eyepiece is acting as a simple microscope, in which the simple microscope is going to form an image at infinity when the object is placed at principal focus. And you can observe that the objective lens is similar to that of the objective lens that we studied in the compound microscope case, so that they also we just derive the expression just by using V by U. So here now let us move towards the linear magnification. The linear magnification of the compound microscope is written as a product of this magnification of objective lens and the magnification of eyepiece. Now here, eyepiece is simply acting as a simple microscope. To find ME, now let us find ME, my dear students. Eyepiece is going to act as simple microscope. ಯಾವ case ಅಲ್ಲಿ, see, before that we studied one case. In that case, we observed that the image is formed at least distance of distinct vision. So in that case, we substituted that ME is equal to 1 plus D by FE. But here this eyepiece is again acting as a simple microscope, but the image is formed at infinity. So the formula changes. So that the eyepiece acts as simple microscope. Yes, it is acting as a simple microscope. Then what is the formula in case of a simple microscope? When the image is formed at infinity, so that is simply written as D by F, where D is said to be the least distance of distinct vision, and FE is considered as the focal length of eyepiece. Take it as equation number 2. So then let us find M naught. To find M naught, so by definition you know that M naught can be written as V naught divided by U naught. Let us observe it carefully. What is V naught? V naught is called as the length of the microscope. So just substitute V naught is equal to L, that is called as the length of microscope. And what is U naught? You are measuring U naught opposite to the direction of incident ray. So the sign convention becomes minus. So U naught is equal to minus F naught. Right. Now M naught is equal to minus L by F naught. Take it as equation number 3. Now let us substitute equation 2 and equation 3 in equation 1. Yes. Put 2 and 3 and 1. What will get? M is equal to minus L by F naught into D by Fe. So this is the final expression for the linear magnification of a compound microscope when the image is formed at infinity. So my dear students, where L is the length of a microscope, F naught is the focal length of objective lens, Fe is the focal length of eyepiece, and D is the least distance of distinct vision. Then what does this negative sign indicate? See my dear students, you can observe that. You know already, by considering convex lens, we have written the ray diagrams. In case of while writing of the ray diagrams, we just even describe the nature of the image form. Suppose if the object is placed at principal focus, the image is formed at infinity. What is the nature of the image in this case? It is real and it is inverted and it is enlarged, so that the image form is inverted at infinity. So that inverted image gives you the negative sign here. So that the negative sign indicates that the image form is inverted. Image form is inverted. Right. Yes. This is about the two different cases of compound microscope. Yes. Hope you got the two different cases of compound microscope. Yes, even with this, we can even derive the linear magnification case just by using the definition of angular magnification. Dear students, you know already that the angular magnification in case of the simple microscope. That is what? The angular magnification is defined as the ratio of tan theta I divided by tan theta naught. Or simply you can say that the magnification m is equal to theta I by theta naught. How to define it exactly with the definition? So we have defined even it in the previous class. That is what the angular magnification is defined as the ratio of the angle subtended by the image at the eye to the angle subtended by the object at the eye. But please be careful, this is only for the simple microscope, but when we come towards the compound microscope, there is a condition 1. Both object and image, object and the final image are considered to be at the least distance of distinct vision. See my dear students, we just defined that the angular magnification definition as we define it in case of simple microscope, but we use the last condition that when both the image and the object are placed exactly at the least distance of distinct vision. Then now let us see that okay, sorry for the interruption dear students. So as I said you that as we did in case of a simple microscope, I am just again moving towards the compound microscope also. I just said you that the angular magnification is a ratio of the angle subtended by the image at the eye to the angle subtended by the object at the eye. But when both the image and the object are exactly placed at a least distance of distinct vision. Now let us move on. So I am just going to write. Yes, take the heading. Expression for the linear magnification of a compound microscope by considering the angular magnification. Now I am just using the two lenses, right? So I am using the two lenses. One is said to be the objective lens. So this is said to be the objective lens, the lens which is having less focal length and the less aperture, and the lens which is placed towards the observer is said to be the eyepiece. So now both the lenses are said to be the convex lens which are placed coaxially. So yes. Now according to the working principle, so see I am just going to place an object, say AB. The object is at a distance of u0 from the optic center of objective lens. Then the object is placed just beyond the principal focus. Now my dear students, please be careful. I am using a parallel beam of light. When a parallel beam of light is allowed to fall on the lens after refraction, it passes out, see, after refraction, it passes out through the principal focus of the lens. Through the principal focus of the lens. Right. That's enough. Next I am using another one ray. The ray which is passing through the optic center. It passes without refraction. So now you can observe that we got an image which is real and inverted. formed on other side of the convex lens, that is beyond 2f0. Let us name it as a dash b dash with height a dash h dash, where h is the height of the object AB. Right. Now, then what is this? The distance between the objective lens and this image formed by the objective lens is called as the image distance V0. Whereas here is the principal focus of the eyepiece, then the distance between the optic center of the eyepiece and the principal focus is called as the focal length of the eyepiece, represented as small fe. Right. And you know that what I said already, the distance between these two, the object a dash b dash and the eyepiece, is adjusted such that we should get an image exactly at least distance of distinct vision. But here, in case of angular magnification, what we are going to consider, see, now the object is exactly assumed. See, I am just assuming that the object is placed at, see, I am just going to consider it as the object is placed at the least distance of distinct vision. So this distance is called as the least distance of distinct vision. Now, where is the object? The distance between this object and this optic center of the eye is called as the object distance of an eyepiece, that is written as UE. Right. Now, please be careful. Now the object is here, but this ray after refraction, so it undergoes a refraction in this way and it meets at a point. Yes, it meets at a point. Whereas the ray which is coming from the object placed at the least distance of distinct vision, it is going to undergo the refraction and it is going to meet at this point. Then the image, the final image, let us say that final image as a double dash, b double dash, is formed at a distance of least distance of distinct vision. See, hope you got. So here the lens of coaxially be placed. Then one is said to be the objective lens with less aperture and less focal length, and the other lens with a greater focal length and a greater aperture is called as eyepiece. So what I just did, I just placed an object beyond the beyond the f0, just beyond the f0. Due to that, with a height h and object distance u0. So it formed an image which is real and inverted a dash b dash at a distance of b0 from the objective lens. Whereas this image formed by the objective lens serves as an object for the eyepiece. Whereas now, what actually this eyepiece is going to do, if we just adjust the distance between them, it forms an image at least distance of distinct vision. But according to the linear magnification case, according to the angular magnification case, we should assume that the image formed, see, right, the image formed by this lens is exactly at the least distance of distinct vision, as well as the object should also be at the same distance. So now the angle subtended by the final image is called as theta I, and the angle subtended by the object is called as theta naught. Now let us use the definition of angular magnification. By the definition of angular magnification, it can be written as the ratio of theta I by theta naught. Then for small angles, for smaller angles, theta can be written as tan theta I and theta naught can be written as tan theta naught. So m is equal to tan theta I divided by tan theta naught. Now I want to calculate the value of tan theta and tan theta naught. So by using a figure I am calculating it. So from figure C, which triangle I am using to calculate theta naught? I am using a dash. See, I am using a triangle. Let us name it here. So this one is B double dash. A double dash. And this is B double dash. Yes. Right. So you can observe it carefully. I am going to point it as P. So P, B double dash and O. Right. P, B double dash O. Otherwise I will call this one as E because the IP is E and the So because it is O for optic is objective lens and E for iris. No issues. Now P, B double dash E. P, B double dash E. So P, B double dash E. So here theta naught we have tan theta naught is equal to tan theta is equal to opposite by adjacent. Which one is opposite? PB double dash is opposite. EB double dash is adjacent. So let us write it. So PB double dash is opposite. PB double dash is opposite. What is an adjacent? EB double dash. Right? I will just write it. Yes. See what is the distance between E and B double dash? It is D. So I am just writing it as D. Then what is P? B double dash? PB double dash is height of the object. PB double dash is height of the object. So I am writing it as H. Hope you got this? Then similarly, I am using a triangle A dash B dash E. From the triangle A dash B dash E. So tan theta I. Again opposite by adjacent. Opposite is A dash B dash. Adjacent is EB dash. Right. A dash B dash divided by EB dash. So what is EB dash? EB dash is UP. EB dash is UP. That is what the object distance of eyepiece. What is A dash B dash? It is H dash. Right. Yes, students, hope you got. H is the height of the object. H dash is the height of the image. Right. Now let us see. Let us substitute this in this formula. So what will happen? Therefore, m is equal to what is tan theta I? Tan theta I is h dash divided by ue into what is tan theta naught? H by d. So if I just take it reverse, so it becomes d by h. So now I am just replacing it. So we can observe it h dash by h into d by ue. My dear students, height of the image to the height of the image, height of the object, height of the image to the height of the object is called as a magnification for objective lens, and the least distance of distinct vision where the image is formed, that is V divided by U. U is the object distance, D is the image distance. See, you can observe. See, this is for objective lens. So H dash is the height of the image, H is the height of the object. So then H dash by H is called as magnification of objective lens into what is this D by UE? D is the image distance, because image is here. D is the image distance divided by the object distance, called as a magnification for eyepiece. So right, hope you got. So finally we came to know that m is equal to m naught into me. This is what the formula that we used to deduce the expression for the magnification in case of compound microscope. Just my dear students, now let us cross verify it. See, now when we just use the angular magnification and we came towards the linear magnification case. That is what m is equal to m naught into me. So m is equal to, what will be the formula for m naught? See, I just written it as h dash by h. See, I am just cross verifying it. So h dash divided by h into, yes, here it is d by ue. D divided by ue. See, my dear students. So as I said you before, h dash by h. So in place of h dash by h, even we can write it as v by u. And eyepiece is going to just act as my simple microscope, so that in place of h dash by h, I can write it as minus L divided by F naught, and in place of ME, I can write it as 1 plus D by FE. Right, because eyepiece is going to act as simple microscope, and the M naught, that is what the objective lens, is just going to form the image of an object just by using the magnification formula, that is M is equal to V by U. So finally we got the expression M is equal to minus L by F naught into 1 plus V by Fe. See, we just use the angular magnification and we just deduce that the linear magnification, which is equal to the product of M naught and Me. Dear students, what this negative sign indicates? The negative sign indicates you that the final image here, the final image A double dash B double dash, which is formed by this entire compound microscope, is inverted. And one thing, always the magnification of a compound microscope. Magnification of a compound microscope is found to be equal to 1000. Is found to be equal to 1000. Keep this in your mind. So just today we discussed the three concepts, that is what the magnification in case of a compound microscope. When the image is formed at least distance of distinct vision, and we just considered that the linear magnification case in case of a compound microscope where the image is formed at infinity, and the last thing we just deduced the expression for the linear magnification of the compound microscope just by considering a definition of which one? Angular magnification. So my dear students, in this the last derivation that what I discussed is not that much important, but it's helpful for your competitive examination. But at first what I discussed the two different cases. In that case we got M is equal to minus L by F naught into D by Fe, and another one is M is equal to minus L by F naught into 1 plus D by Fe. Those two derivations are very much important and definitely will get those questions in your examination. Thank you dear students. Have a nice time.